All right, we got Kenneth here. Great. Good. Hi, I'm Rich Stromberg. I'm the chair of the PV Technical Division at ASUS. I'm not sure where Michael Kempe is today, but we're going to go ahead and get started. If he jumps on here, we can have him present his slides too, and I've got some Q&A on stuff. So today, I'm going to share now. Let's see, we will share the application here. Okay, can you see my presentation?
Yep.
Okay, great. All right, so we're going to talk about backsheets. There's a lot of focus on cells and efficiencies, and there's good reasons for that. It's really what's driven the the adoption, the widespread adoption of solar photovoltaic modules. But often overlooked are the balance of materials that are used to build PV modules. Things like encapsulants, edge seals, junction boxes, cables, connectors, and the backsheet. And backsheets are actually quite critical. And it's these balance of materials that sometimes contribute contaminants and other issues that will affect the safety, the reliability of modules long term. I wanted to cover those and make people aware of this. So I'll give you background and we'll talk about how certain backsheets may or may not degrade, and then what we know about backsheets today, because there's been quite a lot over the years. First we'll go over a few things of how to join ASUS, and then I'll give you some background and we'll take it from there. So if you are not already an ASUS member, it's real easy and very affordable. We have online only memberships that are extremely affordable. And here's the link. So you can just go to the asus.org website, and then there is a join, renew, donate button. So I encourage everyone to join if you're not already a member. Okay, so backsheets. Uh, a couple of purposes. One is to protect the silicon cell itself from external elements. You don't want moisture condensing on the cells. That would start to cause corrosion and other types of damage to the actual silicon cells. So we have this protective barrier. It is not a hermetic seal, though. So I should point out that there is a rate of diffusion through that material, and although it varies from one backsheet type to another, but it's not uncommon to have a fairly porous backsheet such that if your humidity today is 30%, what the cell sees would be about 30% humidity. If tomorrow it jumped up to 70% within about a day's time, if it stayed there, the backside of the cell would see 70% humidity, relative humidity. So there is some transfer of oxygen, everything that's in our air. So a lot of nitrogen, 21 or so percent oxygen, some trace elements, and of course the moisture that's in the air. The other thing that's very critical is that the backsheet is your electrical insulation for the cells. It's just like an extension cord you might use out in your yard. The rubber insulation on that is what keeps you from getting shocked. So that's super important. And if you're just working with a single module, it might be 35 to 50 volts. Now we have strings of modules. On a residential system, it could be 600 volts, commercial system, 1,000 volts, and utility scale up to 1,500 volts. And so we want to protect people from that voltage, as well as not create any situation where the current moving through the cells and the voltage can arc over to the metal framework of how the modules are mounted. Um, and then I'll just point out that when the integrity of the back sheet is compromised, this can cause electrical shock to people operating, maintaining the array, or arcing. That can cause things like rooftop fires or wildfires, those kind of things. So here's a source for some of that background information. Okay, first we'll talk a little bit about cracking. And this has been observed in multiple types of backsheets, including polyamide, which turns out is the most common for severe cracking, but it's also been seen on PVDF blends, polyethylene terephthalate or PET. And so you can see it on all sorts of materials, but polyamide, I'll show you some photos, has been very notable. The cracking can commonly appear in multi-layer, so you might have a EVA, ethylene vinyl acetate, which is the same kind of material that we use to encapsulate the front and the back side of cells on some modules. There's other materials they use, but EVA is a very common one. So you might see a PET layer, and then EVA. And my assumption is the EVA is actually on the very external of this, of that particular one. PVDF tends to crack more in dry environments. So maybe you're in the Southeast, you don't really see anything like that. But if you're in Arizona, Nevada, those kind of locations, you might see more cracking there. And then, yeah, Mitterhofer found that cracking on the AAA type back sheets, which is a co-extruded polyamide, can get very deep and extend completely through the back sheet material, which causes a failure. Now, the module might still perform, but it now fails the safety test that is used to qualify modules to be safe to put in operation. And then same treatments on a PPE backsheet, this PET EVA, might only reveal very thin superficial cracking of that outer EVA layer. And I'll show you a photo of what that looks like. So here is a AAA backsheet. And you can see it's real obvious to tell here, if we were looking at the front side of the cells, we would actually see three bus bars running from top to bottom because that's the stress point as the backsheet material, as it comes over the rear of the ribbon tabs that extend from the bus bar front side down to make contact to the back of the cell. There's higher stress at that point, kind of runs over a ridge. And so over time, it has developed a stress crack. And you kind of wonder, well, how deep does that go? Well, this spot here tells us that at least at this location, it's kind of a brownish color. And we know that the backside of a metal, we have silver. Silver oxide, once it's thicker than about 200 microns, it becomes brown in color. So it's just like tarnish, like your grandparents' nice silverware or silver gravy boat, things like that. You'll see they'll get some tarnish and it'll be brown colored. So this tells you that uh, uh, air with moisture in the air has been able to, at this point, make contact with that backside metal of silver and start to oxidize that silver. And so you're actually seeing silver oxide extrude out through the crack and is visible here on the back sheet itself. So here we know there's at least at this point, there is absolutely no insulation left. And if you were, say, if you had a foggy morning out at the array, or just say you hit dew point, it's warmed up, but you still have moisture condensing. That is a short path from the cells, not only on this module, but all the modules strung together, where you can have arcing if there is a metal framework from the mounting structure. So this is polyamide. I don't know what led to polyamide being somewhat widely adopted from 2012 to 15. It was a very popular one, not with all manufacturers, but with some. A lot of these got out into the field, and it wasn't until several years in the field that these cracks started to appear. You would have thought that the IEC testing, I think it's the 61250, would have stressed the module enough to create these backsheet cracks, but that testing did not do that. So, anyway, real problem with those. The most popular type of backsheet up through 2020 has been have a PET layer that's then laminated with PVF or PVDF. And I'll show you, I have a nice graphic that shows you all the different types. So, because you're probably wondering, all right, he's throwing a lot of letters at me. I'll show you that table and that graphic. So today there's a new type of backsheet, CPC, which stands for some kind of coating, which can vary, a PET layer, and then another coating, so kind of sandwiched. Double-sided coating material. It's the most common type of backsheet across the main Chinese module manufacturers today. These have the advantage of lower cost. They lack gaps that can be common with other multi-layer lamination, and I'll show you photos of one of those. And there's a potential to adjust the material ratio, especially in the coatings, so you can be optimized for different operating environments, drier, wetter, cooler, hotter. But as of yet, even though there's that potential, we don't know of anyone who's actually done that yet. Um, so modules with CPC backsheets have passed the IEC testing, although it's the same testing procedures that I believe they haven't changed since the polyamide was quite popular. But these do not guarantee long-term performance reliability. There could still be sensitivities. So a great fella out of Europe, Gernot Oreski, he's with the Polymer Competence Center, and he did a literature search of all published literature on PV backsheets from 2018 to 2023. It was a total of 296 papers. Out of that, only three of those papers made reference to CPC backsheets. So the point we're trying to get at here is CPC backsheets aren't necessarily bad. They're being used a lot, but we just don't have data that really shows much study on those. So they might be fine moving forward over the next 25-year lifetime of these modules. There might be problems. It's just an unknown. And again, I think I said 2015, 2012 to 2015 for the AAA polyamide backsheets. I said that wrong. It's actually 2010 to 2013. And now we know those are a higher rate of failure. People aren't using them anymore, but you may encounter modules in the field with those. And you'll know it right away when you see it. It will typically be on every single module if you see it at all. Okay, so here's a nice little graphic that came out a couple years ago from Taeyang News. I really like it though. So it's kind of the cheat sheet or the program for when you go to the baseball game to find out who are the players and what are their stats. And so on each of these, there's the air side, so that would be the outside layer, the core layers in the middle, and then the cell side is what actually makes physical contact either with the silicon cell itself, or there might actually be an additional encapsulant layer on the backside of the cell between the backsheet layers. So here there's this older Tedlar, and you can see there's Tedlar, PET, and then Tedlar. There's this Kynar, which I don't know that I've run into. There's several other types here with polyethylene on the cell side. And then we get to PDF, PVDF, and PET. Here, coding, that kind of tells you there's some variation. Another thing to know on this graphic is these different layers are not all the same thickness. It can vary. I can tell you for sure that if you see a polyolefin or an EVA, then that's a very, very thin layer. But some of these other coatings, I just I don't know enough on all the various types to know how thick those are. The other thing that's a true statement would be whether you're talking PVDF or Tedlar or a PET, all these materials. The chemistry can change a little bit from one supplier to another. So it's not all exactly uniform, which kind of creates some variability in the manufacturing supply chain, and that could cause some issues of slight variation, especially with some of these newer high efficiency cells, either heterojunction technology or the latest PERC or TopCon cells. They might have some sensitivities to some of the materials here. And so variation is, it's really important to work with backsheet suppliers if you're making PV modules to get them to control their inputs. And if they make any changes or you make any changes on the backsheet, to rerun some of these extended life tests to stress under damp heat and temperature cycling and things like that. Here's the CPC, that's the most common. And then here's like all polypropylene. So some of the defect types you might see. Here's a different kind of cracking, and it actually is occurring in between the cells. So that's where the stress point was on this particular backsheet material and module. Here's just a scratch with kind of a gouge, a divot that's kind of peeled that up. And then this is an effect that's called chalking. UV light over time can break down different types of back sheets. And if you run your finger across them, you should not have the system energized when you do that. So turn off your inverter or your DC combiner. So in case there was a problem, you wouldn't get electrical shock. But this is kind of medium to medium heavy levels of chalking here. It's really not known, though, how much chalking it takes to start uh, degrading enough where you're losing that 600 volts of insulation capabilities or 1,000 volts or 1,500 volts. But you will see this on some modules. Other module back sheets, the very glossy ones, you probably won't see anything at all, at least for the first 10, 15 years. They could still potentially, depending on the material, break down over time. Now, some of you are probably wondering, well, wait a minute, this is on the back side. How are we getting UV light to degrade the back sheet? Well, that's because the ground has some degree of reflectivity. Most grasslands and sand, dirt is about 18% albedo. So 80% of the light coming in will bounce off the ground back onto the rear side of the module. Part of that's why we do bifacial modules, get that extra energy from other photons coming in on the backside. So that's how you can get degradation over time and breakdown of that backsheet material. This is very common with sharp PV modules. They had adopted a backsheet that has that outer EVA layer, and here you can see it's actually bubbling up. It's clear, and so if I back up, let's just go and see which might be the could be polyolefin, but there's also an EVA layer as well. So I can't tell exactly which type. This is also a different kind of issue where you kind of see these ridges, and this is that EVA material also. It kind of, I don't know, having not seen these modules when they were brand new, did these ridges already exist? Or is that something through thermal cycling over time and longer term exposure to UV light reflecting off the ground causing that? I only saw these after they've been in operation for about 10 years. Here, the actual little ridge that's kind of built up of that clear encapsulant layer on the outside. It's cracked and it's actually flaked off. And now we're looking at the layers underneath. Here's some other signs. This is actually the back sheet probably isn't a problem. It's that there's an issue with the front side of the cell. Maybe it's silicon cracks. If you were to look at the front side, I bet you'd see burnt front encapsulation. But this cell has been getting really hot. It's probably got cell cracks, and one of these electrical paths may no longer be working to connect this cell to the other. And so you get a high resistance path. It heats up the whole silicon cell, and we start to see browning, burning of the backsheet layer. The longer it operates like that, the darker that will become. This is a little more subtle, but these also, it's a different type of backsheet, and it's actually cause kind of some bubbling out of that thin encapsulant layer that's on the very outside, but you can also see some browning of the underlying back sheet too. All these photos, like if you see this on a module, you need to retire it. Don't reuse it, send it to recycling. This is fine. This is not a problem here. These are okay to leave in operation if you don't see any browning of the cell, but I wouldn't really recommend those for reuse. But if they're on your array and they're working fine, it's okay to leave them in place. Okay, here's another type, quite a bit more subtle. And so the sun is shining in from the front side. You can see these little bitty cracks in between the cells where it's a little bit lighter. And then even where the silicon cell is blocking the light, you can see it's almost like there's a stress point around this little tab that connects some of the cells as they lay them out to place them on the front glass and solder all the cells together. They have these little tabbings that hold them in place. Well, that's created some stress, and this is called interlayer cracking. So this is most likely it's an encapsulant layer on the cell side, and then we have the rest of the back sheet, and it's starting to cause some cracking. Um, there's one entity that has published saying that these interlayer cracks cause burnt cells. I have never seen that. I did analysis at this site that had quite a few modules. Electrically, they performed fine. There were lots of other modules with burnt cells for other reasons, but none of the modules that had this particular interlayer cracking had any burnt cells. So I think they're mistaken on that. And until I actually see some data that correlates at least these cells, this interlayer cracking to burnt cells, I'm treating it as a cosmetic defect. Here's a kind of a closer look at it as well. All right, here's this is another sharp module, and you can see how we have bubbles all over the place here. And that right away tells us, oh, there's a rear encapsulant whenever you see this kind of bubbling here. Again, if this is working fine, it's okay to leave it in place if there's no discoloration. And one thing you might notice is, see, there's this cell here right by the junction box. It's white, whereas all the other ones are a tan color. Why might that be? Well, um, UV light has caused the the encapsulant layer that's on the outside to gradually discolor over time and turn towards light brown color. But if oxygen is in on the inside of that, then oxygen, if it's allowed to diffuse through that layer, it will actually have an effect called photobleaching and will reverse that encapsulant discoloration. Well, around where the junction box is, yes, it's sealed as it's actually connected to the backside of that cell, but inside the junction box itself, there's still path for air to get in there. And so this cell itself has had photo bleaching, probably at the same rate as just the UV aging of the other cells. So you'll see that one is a different color, and that's why. Here's another one, and you can see, yeah, here's the same effect of the white cell on the back sheet by the junction box, but there's these three, almost four, that are white, and that's because this cell here, there's it's burnt through, and there's actually a path for oxygen to kind of get in here and photo bleach. The fact that you see these burns, the burn regions on the back sheet, you should take this module out of service and send it to recycling. It is a shock hazard. So that's what I've got on um, as far as background and defect types, those kind of things. I'm going to pause for just a minute and let's see if we have any questions from folks. Okay. Oh, actually,
Um,
we have quite a few in the chat. So let's kind of go through and let's see. So Drew's saying they removed about 50 modules from Boston Harbor Island of stainless steel back sheets. That's interesting. Now, I can oh, and that was 20 years ago. So, Drew, do you know what module types those might have been that had stainless steel on the back? Because I can tell you.
It's a long time ago. All I can remember, I believe, is they were, I think, French or European origin. I think
Mhm.
they were installed by the Coast Guard. I don't think they're the Arco 16 3033s or whatever, which are
Right.
durable, but they had to be removed for that reason. The other funny story there is Rich was the boss. So after he got Henry and I started taking things apart, he went off and took a nap unbeknownst to us.
I have seen Spectrolab early on in development of terrestrial modules. They used a metal backside as well, and that didn't really last long. There might have been some military requirement where they thought they needed a metal backing to the cells is probably misguided. Well-intentioned but misguided is what I would guess. And then let's see, what else do we have here? Um, So, okay, Drew also mentions bifacial modules. And so and I was hoping that Michael would be on here to talk with us about the properties of bifacial back sheets. Most bifacial modules now have glass, the cell, a front glass, the cell, and a rear glass. And so and they call it glass glass. But there are still certain models of bifacial modules that have a front glass cell and then a rear transparent back sheet. And so I don't know the properties of that, but it does allow transmission of light through that back sheet. So
I
um,
am here online. I got here late. I didn't get the
okay. Oh,
note. I'm not prepared to do anything. I didn't get the meeting on my calendar until today, so apologies
okay.
for that.
So, thanks for joining us, Michael. What can you tell us about the properties of bifacial backsheets?
Well, everyone I've seen has a fluoropolymer outer layer, and usually you try and make the fluoropolymer super thin because it's expensive. Um, and I've worked a little bit with DuPont's clear Tedlar. Um, and I mean, the big concerns with them are, like you just showed a picture, you scanned by a picture of chalking. You can't have chalking if you need it to be transparent, though they won't chalk because they don't have filler in the same way, but they could oxidize and stuff like that. The CPC material, I'm somewhat concerned with that. I haven't seen a lot of any data on field exposure, but maybe I've just missed that. The concern is it can be done. The question is, have they done it correctly? Because that PET layer is not going to have any substantial blocking of the UV light coming to it. And PET is very easily oxidized to produce chromophores and turn yellow. So that's a concern. It's on the backside, so it would happen roughly 10 times slower. And it's a concern that's there, but they're doing it because that's a super inexpensive material to be fully transparent, that the coatings are like 25 microns thick or something like that. So they're just
Okay.
they're just nominal.
Okay. Oh, yeah, because I was wondering what is that coating and how thick they are. And to your point, I don't know if you were on when I had
Yeah, I
this
was
book.
there.
Yeah, so Gernot saying, hey, there's only been three papers
Yeah.
out of 296 with any reference at all. So
That's
it's
because
one of
it
those.
went from complete. Yeah, I was. He talked about that at one of the workshop I was at a while back, and it just came. The CPC material just came out of nowhere. It wasn't anywhere, and then 2 years later, it's like half the market, and it's just because it's super inexpensive.
Yeah. Um, let's see. Timothy McBride asks, see, he says, does PVT cells help protect against backsheet defects that are heat or insulation related? I'm not familiar with PVT cells. Tim, what are those?
Photovoltaic thermal cells, where you put some kind of tank on the backside of the PV to absorb the waste heat from the backside.
Oh,
And of
okay.
course, that creates differential heating and cooling on the backside.
Mhm.
There are a few manufacturers of those, and they would be the best source of information on what effect they have on the long term durability of the PV.
Yeah. Okay. I think it might help. I would guess that it doesn't make it completely immune if you have a hot cell for reasons of, say, cracking or misaligned ribbons, soldering those, anything that's creates a high resistance path. But it probably still helps, is what I would guess. Okay. Drew asks, do seemingly innocuous things like labels cause differential heating and backsheet issues? Um, it's minimal, but yes, you do. If you have a thermal camera, you can actually, and it depends on what they make the label out of. There's a few variations, but I've certainly seen where it's a little bit thicker, and so a little bit more thermal mass, and it's a little bit slower to dissipate heat. You see that effect much greater at the junction box. So especially the older style that, in fact, like the ones I showed on the Sharp modules, it's right behind almost the size of one of the cells. And from the front side, if you've got a handheld thermal camera or you're doing drone thermography, you can certainly see that that cell is going to be hotter than the others because that's a appreciably larger amount of thermal mass that's building up there, and so you will have that. Um, let's see what else we have, and then. Yeah, Timothy's talking about warranties generally cover backsheet damage such as yellowing, cracking. I can delamination. I can tell you for sure that like those modules with the polyamide deep cracks, those were covered under the manufacturer's warranty. So we have that. Um, Michael, I've got a couple other questions. Uh, can you talk a little bit about more about chalking? And I just kind of generally said UV uh, uh, degrade cause UV light causes that to degrade, but can you talk at all about a little bit more of what's going on there? And does chalking ever get serious enough to be a safety or reliability issue?
Okay. Yeah. So chalking, that's where essentially the polymer matrix is decomposed and to the point of essentially being removed. Uh, and part of that can be augmented by the photocatalytic effect of titania. I forget which one. There's two types of titania. One is much more photocatalytic, but both of them are. There's a lot of work that goes into mitigating that effect. So that's what's going on. And they've DuPont did some work a while back where they looked at the slow erosion of a backsheet over time because as you start exposing the titania, it kind of comes off. But over 40-50 years, it was a few microns of Tedlar that was going away, and some of the other materials were, the Kynar was having a little bit more. Well, I don't know, I forget if it was more or less, but it was similarly showing some loss of material. What they were doing to measure the change in thickness is they looked at the thickness of the Tedlar underneath the label versus in the open area. And so you can get a direct measurement of the erosion. So it's a slow erosion problem. I've never seen anyone report it getting to the point of actually causing failure.
Okay. Jumping down some then, so you use the term titania and so my question is, what is the backsheet filler? I use the term titanium oxide. So I'm assuming it is not titanium oxide. It's
Well, that's
something.
titania.
Okay, okay. So it's straight titanium, but then when you get that chalking, is it still just titanium or is it oxidized at
Oh,
all?
it's titanium, titania. I'm not saying
Tit-
titanium, I'm saying
yeah.
titania, which is, titanium oxide. Um,
Oh, okay. Okay.
and one thing to remember is most materials use titania, but uh, Tedlar uses a barium sulfates. It gets away from this photocatalytic thing,
hmm
but it's more
So,
expensive.
okay. And then, of course, my following question is, well, so Titania is there. Why isn't it mentioned along with the polymers when I look at backsheet names descriptions?
Oh, well, it's just one component in the polymer matrix. I mean, there,
Okay.
there's a lot of stuff in there, and nobody's divulging what's in there. Though that one's really easy to detect. You can tell if it's titania or barium sulfate by just doing a FTIR,
Okay. Which is a Fourier transform
infrared
infrared. So
spectroscopy.
it's yeah, infrared. Expensive tools. If anyone has a used one, if they're upgrading, I would love to get a used one of those. But um, yeah, so in fact, that's another question that I had is let's see. I thought I had a question of oh, yeah, the very top one. How can we tell what type of backsheet material is used on a particular module? Um,
Yeah,
and I'm assuming a
APR
lot of times
FTIR will do
we're
it.
not really sure, but yeah.
But you can tell it's easy to tell what the materials are, but who made it is a whole different story.
Okay. And when you use the FTIR, are you only looking at the outer layer or can you tell the core and then the cell side layer as well?
Well, the spot size for that is about a millimeter diameter. So
Hmm.
if you can cut into it, then you can get the other information. But
Okay.
you have to cut it apart.
Okay. Um, the bubbling that I showed on the back sheets, that I seem to see that a lot more with like on sharp modules that have an encapsulant on the air side. What actually causes that bubbling?
It can be a lot of things. You first have to ask which layer is bubbling. And so sometimes, and it depends on how it looks. If the bubbles are exactly around just the cells, then usually that's a delamination on the back sheet, because once it gets to the encapsulant between the cells, it's not delaminating anymore. So that's and the old aluminum back surface field modules, I saw a lot of delamination on the back sheet. That's the encapsulant is delaminating from the cell. It doesn't have anything to do with a bad back sheet. But the other things that can happen is any one of the layers within the back sheet itself can delaminate.
Okay. How is it? So I showed the signs of deep cracks from extruded, co-extruded polyamide. How is it that the AAA back sheets were adopted by multiple manufacturers and only later found to be sensitive to this deep cracking?
Oh, because the qualification tests at the time just sucked. I mean, they straight up didn't catch it. The to I developed a test, the solder bump test, where you laminate the material with a piece of solder wire in there, and you laminate with encapsulant to a piece of glass, and then expose it to thermal cycling and UV radiation. You have to do all of that to see this failure, and it'll catch all kinds of cracking failure and all kinds of known bad materials. So why didn't they catch it? It's because, first of all, the UV exposure, the preconditioning and the qualification tests is equivalent to a few weeks, not nearly enough. Then you do 200 cycles, which is maybe enough. If you had enough UV light, you might catch it. And then my presumption, I don't know this, but the manufacturer, or I believe that they just tested their freestanding films, because what we found with freestanding films is they didn't they retained their uh, tensile strength after time as a freestanding film, but their elongation to break is what really dropped off. So it's just the tests were just not adequate, didn't put the right stressors on it to cause it to fail.
Okay. And so now on module qualification tests, are they using a newer stresses that should catch at least the polyamide type of failure?
So 63209, yes. 61215, maybe. The
Okay.
test takes, like, to do it properly on a full size module takes 6 months. There just wasn't
Yeah.
an appetite for that.
Okay. Um, what types of back sheets are needed for heterojunction technology and other high efficiency cells? Because it seems like I know looking at say Sanyo modules, Panasonic and Sanyo that used heterojunction cells, their back sheet has like a silver color, and I'm wondering, are they trying to make closer to a hermetic seal where you don't have humidity from the air kind of diffusing through the back sheet? And like TopCon cells, do they have particular sensitivities that they need a less porous back sheet or just other materials?
So this is a good question. Why they're doing it is hard to say. When you say silver, you're not just talking about a mid layer in the back sheet. You're talking about, it looks silver from one of the sides.
Correct. Yeah, when you're standing on the backside of of the module, it definitely it looks silver.
Okay. So most usually, so that means there is a metal layer in there. It's most likely an aluminum film. Usually, those aluminum films are 25 microns, and people do that because they want to keep the moisture out, or minimize it. Uh,
Mhm.
there's still going to be moisture coming in from the sides, and that's going to it'll keep the moisture out, and it should make it a little bit more stable. And that's what they're doing. It does require you to be a little more careful as far as electrical insulation, because you got conduct conductivity the whole way. And the reason
Okay.
to use so any burnout can go to ground real quick and really easily. Whereas some of the burn marks you showed in some of your pictures, while they're not safe to go and touch, they are most likely not a they're not going to cause ground faults in the mornings. But
Okay.
people are using the polymer with the metal back sheets because they want a lighter weight module, and they probably have like a 3 millimeter piece of glass in the front, which is a little more durable with respect to hailstones.
Mhm. Um, so we've talked about silver metallic back sheets. The black back sheets that you might see on, I think more on modules for residential use.
Yeah, that's the only
Yeah,
place I've ever seen black. It's for aesthetic reasons,
yeah.
because
And
it,
and
it
what?
takes out about 2% of your, well, older cells it was around 2. Current cells, they've got them so tight, it at most a percent or a fraction of a percent. There's a slight extra heating, and then there's a little bit of absorption, so you're losing a little bit, but it's like probably on modern modules less than a percent loss.
Okay. And then can backsheet materials influence PID or other degradation modes?
Oh, absolutely. If they put that metal foil in there, you're going to get PID from both sides nicely. Uh,
Okay.
well, it depends on how you might.
Yeah.
Let me backtrack there. You might if it's not well insulated, but it could be sufficient. It depends on how it's constructed.
Yeah.
Probably sufficiently done, but yeah, all the current goes through the glass. Glass is like, 3 or 4 orders of magnitude more conductive than it is PET or most of these polymeric materials. So there's just not going to be much conduction on along the back sheet.
Yeah. One thing I'm wondering about on the bifacial module back sheets is, I mean, you talked to us about that quite a bit, but do you see them on future projects, or do you really see the manufacturers all eventually transitioning to glass modules instead of a glass back sheet module?
Yeah, so the glass backsheet has the advantage that the cells are in the middle between, two pieces of glass, and so they're in the neutral plane. So it has been documented that that does help resist cell cracking. However, with these multi-wire contact schemes, that's not as much of an issue as it used to be when you only had like, especially two, but three or
Yeah.
four uh, bus bar or tabs on the cells. They were a lot more sensitive to cracking than are these newer cell designs. So
Hmm.
they can withstand it. Um, it's a good question what's going to go in the future, because this will always be true. Glass is always going to be cheaper than these polymeric back sheets. They just didn't do it in the past because nobody wanted to deal with the weight.
Yeah. Yeah,
So
it's and you don't realize the weight until you go to a module manufacturing facility and you see pallets of all their materials, and the pallet that's holding the glass is only stacked about, this high or so. Um, and it's like, oh, it's a lot of weight there. So,
Yeah, so this is what I kind of this would be my guess, and this is only a guess and very likely wrong. So I gotta be careful when I say this because I can piss off some of the backsheet manufacturers when I say stuff like this. But I think that in the utility scale, because the modules are getting so big, they need like heavy duty equipment to install them anymore because
yeah.
they're just too big, just physically too big, and they weigh too much. But when you're
Hmm.
going to a residential rooftop, you are you're limited by what one person can safely carry up a ladder. So
Yep.
they're a lot more weight sensitive. They are so I think that that part of the industry may stick with polymeric back sheets. But then, are they going to go for the transparent back sheets? Probably not, because it's on a rooftop. You don't get substantial reflection off the rooftop, so no one's gonna care.
So Kenneth adds on here, he says he's seen discolored back sheets after field aging with a reduced wet leakage resistance. I believe the resistance is supposed to be no at least 40 mega ohms per square meter. So if you actually have 2 square meters on your module surface area, then that would be you would have a resistance of at least 20 mega ohms measured, and that's with there's field tests. There's an ASTM field test where you can actually spray the module front side and back side and then perform your test. Versus there's a qualification test where it actually you immerse the entire module for 2 or 3 minutes and perform your test. But out in the field, it's just a spray down and then you check it. He's saying that the manufacturer makes the argument that the same pass-fail criteria for wet leakage using certification should not apply. Now, I would tend to agree with him that the immersion test doesn't really apply because it's not saying whether a module is safe to use. It's trying to simulate looking forward and doing extra stress to ensure a longer lifetime of meeting the insulation capabilities, the electrical insulation capabilities. But for the ASTM test of spraying it and doing a check, if it doesn't pass, I certainly would not use that module anymore. In fact, in the PV module reuse specification that I co-wrote with Sergio Nules and Arvid Vanderheide, and we had 30 other people helping us on this project, this effort. We follow that. If you do the spray test, and you still have to meet that 40 mega ohms per square meter, but it's not an immersion test. It's a pump sprayer out in the field kind of thing. I can tell you that um, PV recyclers that also have screen modules for reuse and resale, they'll do a module cleaning step to remove the dust, any soiling before they do their flash test on the big table to sweep the power curve. And while they're doing that cleaning step, they'll do the wet leakage, but it's a spray, it's not an immersion. And let's see. Timothy asks, does PV modules on trackers have more damage in general than on back sheets and stationary mounts? I have not noticed that. But in fact, it might actually be a little bit less in its tracking that you over extended periods of time, there's less light coming in from the side that can, UV light to degrade the back sheet, but I haven't seen it be worse. Let's see, Drew says since outputted bifacial is so much more when properly mounted vertically on north-south lines, bifacial will dominate. Anything? Oh gosh, she's talking about carrying solar thermal panels up ladders too. Gosh, that's got to be. really uh, not good for the body mechanics. All right. Well, any other questions? I think we're basically out of time. Um, Thanks so much, Michael, for joining us. Anything Michael said that is kind of reverses or counters something I told you? Michael's the expert. He is more true than I am. So believe him over me.
That's funny. Thank you.
Thank you so much, Rich and Michael. Really appreciate your time and all your expertise. I will send a follow-up on the recording and a couple other things we discussed. But yeah, thank you so much, everyone, for joining.
Yeah, I'm hoping that now we'll look at back sheets with a little more respect and even some awe.
Great.
Okay, thanks
Thanks,
everybody for
Rich.
All
joining.
right. Thank you all. Have a good rest of your day.
See ya.
Bye.